Metal dusting damage mechanisms as a part of high-temperature corrosion greater than 400 degrees Fahrenheit or 204 degrees Celsius. Description of metal dusting damage based on API 571. Metal dusting is form of carburization resulting in accelerated localized pitting which occurs in carbonizing gases and/or process streams containing carbon and hydrogen. Pits usually form on the surface and may contain soot or graphite dust. Certainly. Here's a detailed description of metal dusting damage, an in-depth explanation, overview. Metal dusting is a form of high-temperature corrosion that predominantly affects high-alloy steels and nickel-based alloys used in petrochemical, refining, and chemical processing industries. It involves the progressive disintegration of metallic components into a fine, powdery, or dust-like form, resulting in structural degradation and potential failure of equipment. Mechanism of metal dusting. Number 1 is environmental conditions, occurs under a combination of high temperatures or typically 450 degrees Celsius to 650 degrees Celsius, presence of a carbon-rich atmosphere, such as carbon monoxide or CO, methane or CH4, and or other hydrocarbons, often found in environments with low oxygen levels, which favor carburization processes. Number 2 of mechanism of metal dusting is initial surface reactions. The metal surface reacts with carbonaceous gases, leading to the formation of metal carbides such as chromium carbide, iron carbide. The formation of carbides consumes protective oxide layers that normally prevent corrosion. Number 3 of mechanism of metal dusting is dealloying and selective dissolution. Certain alloying elements, especially chromium and aluminum, are preferentially depleted from the surface due to their tendency to form stable carbides. This depletion weakens the formation of protective oxide scales, exposing fresh metal to further attack. Number 4 of mechanism of metal dusting is formation of metal dust. The metal's surface gradually disintegrates into fine particles or dust. The process involves the detachment of metallic fragments, which are then dispersed in the environment. Continuous loss of material leads to thinning of the metal wall or component. Physical and microstructural changes. Number 1, surface morphology. The surface becomes roughened, pitted, and develops a powdery or flaky appearance. Formation of cavities and microcracks due to stress from material loss and thermal cycling. Number 2 of physical and microstructural changes is microstructure. Presence of carbide precipitates within the metal matrix, depletion zones around carbides, leading to localized weakening, possible formation of porous, sponge-like structures resulting from material loss. Manifestations of metal dusting damage. Number 1, material loss, progressive thinning of the material, which can lead to perforation or failure. Number 2, structural integrity, reduced mechanical strength and ductility, increased susceptibility to cracking and fracture. Number 3, operational hazards, particle accumulation in equipment can cause blockages or contamination. Potential for catastrophic failure if not detected early. Metal dusting is a complex, high-temperature corrosion process characterized by the gradual disintegration of metal into dust due to carburization, carbide formation, and dealloying. It leads to significant material loss, structural weakening, and potential equipment failure if not properly managed. Metal dusting affected material based on API 571, low alloy steels, 300 series SS, nickel base alloys and heat-resisting alloys. There is currently no known metal alloy that is immune to metal dusting under all conditions. Certainly. Here's a detailed explanation of the materials affected by metal dusting damage. Affected materials and metal dusting damage. Overview. Metal dusting primarily impacts high-temperature alloys and metals that are commonly used in environments rich in hydrocarbons at elevated temperatures. The susceptibility of a material to metal dusting depends on its chemical composition, microstructure, and protective oxide forming capabilities. Here's a detailed explanation of the materials affected by metal dusting damage. Number 1, high alloy steels. Types affected of high alloy steels: austenitic stainless steels such as 304, 316, 321, 310, ferritic and martensitic stainless steels, low alloy steels with high chromium content. High alloy steels details. These steels contain significant amounts of chromium or Cr, nickel or Ni, and sometimes molybdenum or Mo, which normally form stable oxide layers protecting against corrosion. In high-temperature, hydrocarbon-rich environments, the protective oxide layers can be compromised. Chromium carbides tend to precipitate at grain boundaries, leading to depletion of chromium in the surrounding matrix, weakening the corrosion resistance. The microstructure becomes susceptible to carburization, leading to the formation of internal carbides and surface disintegration. Number 2 of the materials affected by metal dusting damage is nickel-based alloys. Types affected of nickel-based alloys includes Inconel series such as Inconel 625, 600. Hastelloy alloys, and Monel. Details of nickel-based alloys. These alloys are designed for high temperature and corrosion resistance, containing high nickel and chromium contents. Despite their excellent properties, they are vulnerable to metal dusting in hydrocarbon atmospheres at elevated temperatures. The formation of nickel and chromium carbides depletes the alloy's protective elements, leading to localized corrosion and dusting. Number 3 of materials affected by metal dusting damage is refractory metals and alloys. Types affected are tungsten, molybdenum, and their alloys. Details is, although highly resistant to many forms of corrosion, under certain conditions, these metals can also experience dusting, especially when alloyed with elements prone to carbide formation. Number 4 of materials affected by metal dusting damage is other metallic materials. Pure metals such as iron, nickel, and chromium in pure form can undergo dusting, but they are seldom used in high-temperature hydrocarbon environments due to poor corrosion resistance, and then, alloys with poor corrosion resistance. Materials with low chromium or nickel contents are more prone to dusting because they lack the formation of stable oxide layers. Number 5 of materials affected by metal dusting damage is coated or clad materials. Affected materials because of substrates with protective coatings or claddings may experience damage if the coating fails or is compromised, and then, the underlying material can undergo dusting if exposed to the corrosive environment. Factors influencing material susceptibility. Number 8, chemical composition. High chromium and nickel contents generally improve resistance but are not immune. Presence of elements like silicon, manganese, or aluminum can influence oxide stability. Number B, microstructure, grain boundaries, precipitates, and inclusions can act as initiation sites for dusting. Number C, operational conditions, temperature, hydrocarbon concentration, and presence of other corrosive species such as sulfur compounds impact susceptibility. In essence, metal dusting primarily affects high-temperature, corrosion-resistant alloys such as austenitic stainless steels, nickel-based superalloys, certain low and high-alloy steels. These materials are vulnerable because their protective oxide layers are compromised under specific conditions involving hydrocarbons and high temperatures, leading to carburization, carbide formation, and eventual disintegration into dust. Metal dusting. Metal factors based on API 571, process stream composition, operating temperature and alloy composition are critical factors. B. Metal dusting is preceded by carburization and is characterized by rapid metal wastage. C. Metal dusting involves a complex series of reactions involving a reducing gas such as hydrogen, methane, propane, or CO. D. It usually occurs in the operating temperature range of 900 degrees Fahrenheit to 1500 degrees Fahrenheit or 482 degrees Celsius to 816 degrees Celsius. Damage increases with increasing temperature. E. The mechanism of metal dusting is considered to be, number 1. Saturation of the metal matrix by carburization, number 2. Precipitation of metal carbides at the metal surface and grain boundaries, number 3. Deposition of graphite from the atmosphere onto the metal carbides at the surface, number 4. Decomposition of the metal carbides under the graphite and metal particles, and, number 5. Further deposition of graphite catalyzed by the metal particles on the surface. F. In high nickel alloys, it is thought that metal dusting occurs without the formation of metal carbides. G. Metal dusting can also occur under alternating reducing and oxidizing conditions. Certainly. Here's a comprehensive and detailed explanation of the critical factors that influence metal dusting damage. Critical factors influencing metal dusting damage. Overview. Metal dusting is a complex process governed by multiple interrelated factors that determine how susceptible a material is to disintegration under high-temperature, hydrocarbon-rich environments. Understanding these critical factors helps in predicting, preventing, or mitigating dusting damage. Here's a comprehensive and detailed explanation of the critical factors that influence metal dusting damage are. Number 1 is temperature. Key role of temperature are, elevated temperatures accelerate chemical reactions, diffusion processes, and carbide formation. Typically, metal dusting occurs within a temperature window of approximately 450 degrees Celsius to 650 degrees Celsius. Details of temperature are, high temperatures promote carburization and the breakdown of protective oxide layers. Temperature fluctuations can induce thermal stresses, leading to cracks that facilitate dusting. Temperatures below this range may reduce dusting but can still cause other forms of corrosion. Above this range, the process accelerates significantly. Number 2 of the critical factors that influence metal dusting damage is carbon activity in the environment. The key role is the concentration of reactive carbon species such as CO, CH4 significantly influences dusting. Details of carbon activity in the environment are: high carbon activity or a measure of carbon potential in the atmosphere enhances the diffusion of carbon into the metal. Elevated carbon activity fosters carbide formation and carburization, weakening the metal matrix. Environments rich in hydrocarbons or carbon monoxide are particularly conducive to dusting. Number 3 of the critical factors that influence metal dusting damage is alloy composition. Key role is the chemical makeup of the alloy determines its ability to form protective oxide layers and resist carburization. Details of alloy composition are includes: the first is chromium content. High chromium levels promote the formation of stable, adherent oxide scales. And depletion of chromium, the carbide formation, diminishes corrosion resistance. The second is nickel content, enhances ductility and oxidation resistance. The third is addition of elements. Elements like aluminum, silicon, and molybdenum can influence oxide stability. And the fourth is impurities and inclusions. Non-metallic inclusions or impurities can serve as initiation sites for localized damage. Number 4 of the critical factors that influence metal dusting damage is material microstructure. Key role is microstructural features influence the initiation and progression of dusting. Details of material microstructure are includes: the first is grain size. Fine grains may accelerate carbide precipitation at grain boundaries. The second is precipitates and phases. Carbide precipitates such as Cr3C2 deplete chromium and weaken the matrix. The third is grain boundaries, act as diffusion paths for carbon and sites for carbide nucleation, and the fourth is porosity and defects. Microvoids or cracks facilitate gas ingress and localized corrosion. Number 5 of critical factors that influence metal dusting damage is presence and stability of protective oxide layers. Key role is a stable, adherent oxide scale inhibits carburization and metal loss. Details are: oxide formation depends on alloy chemistry and environmental conditions. Degradation or spallation of oxide layers exposes fresh metal. Continuous high-temperature cycling can cause oxide failure. Number 6 of critical factors that influence metal dusting damage is environmental factors. Key role is the composition of the surrounding atmosphere influences dusting. Details are: hydrocarbon concentration. Hydrocarbon-rich atmospheres promote carburization. Presence of sulfur or other corrosive species can synergistically accelerate damage. Oxygen levels. Low oxygen environments favor carburization. Higher oxygen levels can promote oxidation instead. Number 7 of critical factors that influence metal dusting damage is gas flow and turbulence. Key role is gas velocity and turbulence impact mass transfer rates. Details are: increased flow rates enhance the transport of reactive gases to the surface. Turbulence can cause uneven temperature distribution and oxide spallation. Localized high flow areas can accelerate damage at specific sites. Number 8 of critical factors that influence metal dusting damage is operational conditions. Key role is factors such as pressure, thermal cycling, and process duration influence dusting. Details are: prolonged exposure increases cumulative damage. Thermal cycling induces mechanical stresses and cracks, promoting dusting. Pressure: higher pressures can increase gas phase reactant concentrations. Summary of critical factors that influence metal dusting damage. For factor is temperature, it will impact to accelerates reactions. It is described as higher temps promote carburization and carbide formation. For factor is carbon activity, it will impact to drives carburization. It is described as elevated hydrocarbons or CO increase carbon ingress. For factor is alloy composition, it will impact to determines corrosion resistance. It is described as chromium, nickel, and other elements influence oxide and carbide stability. For factor is microstructure, it will impact to affects initiation sites. It is described as grain size, phases, and defects impact carbide precipitation and diffusion pathways. For factor is oxide layer stability, it will impact to protects against damage. It is described as stable, adherent oxides prevent carburization, their failure accelerates dusting. For factor is environment composition, it will impact to modulates corrosion processes. It is described as hydrocarbon, sulfur, and oxygen levels shape damage severity. For factor is gas dynamics, it will impact to influence mass transfer. It is described as flow rate and turbulence affect reactant access and oxide spallation. For factor is operational conditions, it will impact to affect damage progression. It is described as duration, cycling, and pressure impact cumulative effects. Understanding and controlling these critical factors are essential in designing materials and processes that mitigate metal dusting damage, ensuring safer and more reliable operation in high-temperature hydrocarbon environments. Metal dusting affected units or equipment based on API 571, Number A, primarily fired heater tubes, thermowells and furnace components operating in carbonizing environments are affected. Number B, metal dusting has been reported in catalytic reforming unit heater tubes, coker heaters, gas turbines, methanol reforming unit outlet piping and thermal hydrodealkylation furnaces and reactors. Certainly. Here's a detailed explanation of the units or equipment that are affected by metal dusting damage, affected units, and equipment in metal dusting damage. Overview: metal dusting primarily occurs in industrial environments where metals are exposed to high temperatures in hydrocarbon-rich atmospheres. The damage manifests in various types of equipment, often crucial for processes like refining, petrochemical production, and power generation. Number 1 of the units or equipment that are affected by metal dusting damage is heat exchangers. Type affected are shell and tube heat exchangers, and plate heat exchangers. Heat exchangers details: location function includes, used to transfer heat between different process streams, often operate at high temperatures between 450 degrees Celsius and 650 degrees Celsius. Heat exchangers vulnerable areas such as tube surfaces and headers are prone to dusting, fouling and corrosion lead to thinning, leaks, or tube failure. Impacts of dusting on heat exchangers are loss of tube integrity, leading to leaks or catastrophic failure, reduced heat transfer efficiency due to internal corrosion and dust formation. Number 2 of units or equipment that are affected by metal dusting damage is furnaces and boilers. Type affected includes combustion chambers and heating surfaces. Furnaces and boilers details: location function are provide high temperature environments for process heating. Furnaces and boilers details of vulnerable areas such as refractory line sections with metallic interfaces and superheater and reheater tubes. Furnaces and boilers details of impacts of dusting, material thinning and eventual perforation, and increased maintenance costs and risk of fires or explosions. Number 3 of units or equipment that are affected by metal dusting damage is reactors and processing vessels. Type affected such as fixed bed, fluidized bed, or catalytic reactors. Reactors and processing vessels details location function such as facilitate chemical reactions at high temperatures. Reactors and processing vessels details vulnerable areas such as internal metallic components, especially those in contact with hydrocarbons, and reactors and processing vessels details impacts of dusting such as structural weakening, leading to deformation or failure, and contamination of products due to metal particles. Number 4 of the units or equipment that are affected by metal dusting damage is piping systems. Type affected such as high temperature hydrocarbon transfer lines and exhaust and vent pipes. Piping systems details location function such as transport hydrocarbons, flue gases, or process fluids. Piping systems vulnerable areas such as bands, welds, and joints where stress concentrates, and piping systems impacts of dusting such as thinning of pipe walls, leaks, and potential rupture. And increased risk of fires if metal particles ignite. Number 5 of the units or equipment that are affected by metal dusting damage is catalytic converters and reactors. Type affected is catalytic beds and reformers or cracking units. Catalytic converters and reactors details location function is facilitate chemical transformations at elevated temperatures. Catalytic converters and reactors details vulnerable areas as metal supports and catalysts casings. Catalytic converters and reactors details impacts of dusting or structural degradation leading to catalyst failure and loss of efficiency and increased operational costs. Number 6 of the units or equipment that are affected by metal dusting damage is storage tanks with heated sections. Type affected is heated oil or chemical storage tanks. Storage tanks with heated sections details vulnerable areas as heating coils or jackets, and the impacts of dusting are material thinning and potential leaks and increased risk of fire or explosion. Number 7 of the units or equipment that are affected by metal dusting damage is cooling systems and circulating pumps. Type affected such as pump casings and cooling circuit components. Cooling systems and circulating pumps details vulnerable areas as metallic parts exposed to high temperature hydrocarbons. Impacts of dusting are mechanical failure due to material degradation and leakage or loss of efficiency. Number 8 of the units or equipment that are affected by metal dusting damage is regenerator and heat recovery units. Type affected is flue gas heat recovery systems. Regenerator and heat recovery units details, location and function commonly at recover heat from process gases, vulnerable areas such as metal surfaces exposed to hot gases with hydrocarbons, and impacts of dusting is material thinning, corrosion, and eventual failure. Summary table of metal dusting damage mechanisms affected units or equipment. If it is on equipment and or unit is heat exchangers, described as transfer heat between streams. The vulnerable areas are at tubes, headers, and the consequences of dusting are leaks, reduced efficiency, failure. If it is on equipment and or unit is furnaces, boilers, described as high temperature process heating. The vulnerable areas are at heating surfaces, tubes, and the consequences of dusting are thinning, perforation, leaks. If it is on equipment and or unit is reactors and vessels, described as chemical reactions at high temperatures. The vulnerable areas are at internal surfaces, and the consequences of dusting are structural failure, contamination. If it is on equipment and or unit is piping systems, described as hydrocarbon transport. The vulnerable areas are at bends, joints, and the consequences of dusting are rupture, leaks, fire risk. If it is on equipment and or unit is catalytic units, described as catalytic reactions. The vulnerable areas are at casings, supports, and the consequences of dusting are catalyst failure, efficiency loss. If it is on equipment and or unit is storage tanks, described as heated sections. The vulnerable areas are at coils, jackets, and the consequences of dusting are leaks, fire hazard. If it is on equipment and or unit is pumps, cooling systems, described as circulate fluids. The vulnerable areas are at casings, joints, and the consequences of dusting are mechanical failure. If it is on equipment and or unit is heat recovery units, described as recover waste heat. The vulnerable areas are at metal surfaces, and the consequences of dusting are material thinning, failure. Metal dusting damages critical process equipment, leading to safety hazards, operational downtime, increased maintenance costs, and potential environmental issues. Recognizing the units most vulnerable allows for targeted monitoring, maintenance, and material selection strategies to mitigate damage. Appearance or morphology of metal dusting damage based on API 571, number A. In low alloy steels, the wastage can be uniform but usually is in the form of small pits filled with a crumbly residue of metal oxides and carbides. Number B. The corrosion product is a voluminous carbon dust containing metal particles and sometimes metal oxides and carbides. Frequently, this dust will be swept away by the flowing process stream, leaving behind only the thinned or pitted metal. Number C. In stainless and high alloy steels, the attack is frequently local, appearing as deep, round pits. See Figure 4.125, metal dusting of a 304H stainless steel pipe. Number D. Metallography will show that the metal is heavily carbonized under the attacked surface. See Figure 4.126. Carbon steel separator plate in a natural gas preheater showing classical pattern of carburization and pitting. Certainly. Here's a detailed explanation of the appearance and morphology of metal dusting damage. Appearance and morphology of metal dusting damage. Overview. Metal dusting results in characteristic surface and subsurface features that reflect the underlying chemical and physical degradation processes. The damage manifests in various morphological forms, which can be observed visually and through microscopic analysis. Number 1 of morphology and appearance of metal dusting damage is initial surface features. Number A. Surface roughening includes, the metal surface becomes increasingly rough and pitted due to localized attack. Small craters and voids may form as corrosion products and metal particles are released. Number B. Formation of carbonized layers includes, a thin, often dark, carbon-rich layer appears on the surface. This layer may be adherent or loosely attached, depending on oxide stability. Number 1 of morphology and appearance of metal dusting damage is pitting and localized attack. Number 8. Pitting corrosion includes, small, deep pits develop, often initiating at surface imperfections or inclusions. Pits are typically round or irregular in shape. They can penetrate deeply into the metal, compromising structural integrity. Number B. Morphology such as the following. Pits often exhibit a smooth, rounded bottom with sharp edges. The surrounding area may show signs of oxide spallation or surface cracking. Number 3 of morphology and appearance of metal dusting damage is carbide formation and depletion zones. Number A. Carbide precipitation includes, visible as dark, granular deposits within the microstructure. These precipitates are often located at grain boundaries or within the matrix. Number B. Cracks and voids includes, carbide formation depletes chromium, weakening the alloy. This leads to internal cracks and voids that may coalesce. Number C. Morphology, such as, cracks often Follow grain boundaries, appearing as fine, branching lines, voids or spherical or irregular, sometimes clustered. Number 4 of morphology and appearance of metal dusting damage is surface spallation and scale loss. Number 8, oxide scale spallation, includes, the protective oxide layer may peel off, exposing fresh metal, spalled areas appear as rough, uneven patches. Number B, morphology, such as, fractured oxide fragments may remain attached or fall away, leaving a jagged surface, the underlying metal appears rough and pitted. Number 5 of morphology and appearance of metal dusting damage is formation of carbonaceous deposits. Number A, deposits, includes, carbon-rich, soot-like layers or patches can form on the surface. These deposits may be dark, flaky, or powdery, and the impacts, such as, these layers facilitate further carburization and deterioration. Number 6 of morphology and appearance of metal dusting damage is deep penetration and thinning. Number A, material thinning, includes, progressive dusting results in reduced wall thickness. Cross-sections show thinning of the metal, often with layered structures. Number B, morphology, such as, sections reveal a gradient from carbonized, brittle outer layers to the original metal core. Cracks and voids increase in density with depth. Number 7 of morphology and appearance of metal dusting damage is microstructural changes. Number A, precipitated carbides observed as fine, dark particles in micrographs. Number B, depleted zones or areas with low chromium content, appearing as zones with altered microstructure, and cracks and fractures such as microcracks propagate along grain boundaries, pores, or carbide interfaces. Summary of the examples of morphological features: if the feature is pitting, that described as localized corrosion cavities, then the visual appearance commonly such as small, round or irregular holes, may have smooth or rough edges. If the feature is cracks, that described as propagation along grain boundaries, then the visual appearance commonly such as fine, branching lines, often stress-induced. If the feature is void formation, that described as internal cavities from carbide depletion, then the visual appearance commonly such as spherical or irregular cavities, seen in cross-sections. If the feature is scale spallation, that described as loss of oxide layer, then the visual appearance commonly such as rough, uneven patches with exposed metal. If the feature is deposits, that described as carbon or soot layers, then the visual appearance commonly such as dark, flaky, powdery deposits on surface. The morphology of metal dusting damage is characterized by surface roughening, pitting, and spallation, deep internal cracks and voids, carbide precipitates and depletion zones, thinning of metal walls, and deposits of carbonaceous material. These features collectively indicate progressive degradation, compromising the mechanical integrity and safety of equipment exposed to dusting conditions. Metal dusting damage prevention and mitigation based on API 571. Number A, sulfur in the carbonizing atmosphere usually as H2S, forms a protective sulfide that minimizes carburization in metal dusting. It is thought that sulfur retards the carbon transfer from the atmosphere to the metal and suppresses graphite nucleation and growth. For protection, sufficient H2S must always be in the process environment. If the H2S level drops too low, even for a short period of time, damage may occur. Sulfur is a catalyst poison in some processing units, so that the introduction of H2S into a process stream may not always be practical. Number B, there is currently no known metal alloy that is immune to metal dusting under all conditions. Material selection must be made based on the specific application and environment. Number C, an aluminum diffusion treatment to the base metal substrate can be beneficial in some applications. Certainly. Here's a comprehensive and detailed explanation of prevention and mitigation strategies for metal dusting damage. Overview: metal dusting is a severe form of high-temperature corrosion that causes the degradation of alloys exposed to hydrocarbons at elevated temperatures. Preventing or mitigating this damage involves strategies that either eliminate the root causes or protect vulnerable materials. Number 1 of the prevention and mitigation strategies of metal dusting damage is material selection. Number 8, use of resistant alloys such as the following. The first is high chromium alloys. Alloys containing higher chromium content such as 25 to 30% form more stable, protective oxide layers that resist carburization. The second is nickel-based alloys. Alloys like Inconel or Hastelloy are more resistant due to their stable oxide scales and alloying elements. The third is austenitic versus ferritic steels. Austenitic stainless steels generally perform better than ferritic types in resisting dusting, but specific alloying is critical. Number B of the material selection is coatings and claddings. The first is protective coatings. Applying ceramic or metallic coatings such as alumina, yttria stabilized zirconia, can act as physical barriers. The second is cladding, welding or bonding corrosion-resistant alloys onto vulnerable substrates. Number 2 of the prevention and mitigation strategies of metal dusting damage is process design and operating conditions. Number A, temperature control, includes, the first is maintain temperatures below dusting thresholds, operating below critical temperatures or up to 450 degrees Celsius for many alloys reduces dusting risk. The second, avoid temperature fluctuations. Rapid heating or cooling cycles can cause thermal stresses exacerbating damage. Number B of the process design and operating conditions is gas composition management. Number A, reduce hydrocarbon concentrations. Limiting hydrocarbons or oxygen in the environment minimizes carburization. Number B, control of steam and inert gases. Introducing steam or inert gases such as nitrogen can dilute hydrocarbons and reduce carbon activity. Number C of the process design and operating conditions is process optimization. The first is flow rates and residence time, adjusting flow to minimize hydrocarbon residence time in high temperature zones. The second, avoidance of reducing conditions, maintaining oxidative environments prevents carburization. Number 3 of the prevention and mitigation strategies of metal dusting damage is environmental control. Number 8, use of protective atmospheres, includes, the first is inert atmospheres. Shielding the metal surface with nitrogen or helium reduces hydrocarbon contact. The second is controlled oxidizing conditions. Maintaining a slightly oxidizing environment can help form protective oxide scales. Number B, contaminant removal. Removal of hydrocarbons or sulfur compounds. Purification of process gases reduces corrosive species that promote dusting. Number 4 of the prevention and mitigation strategies of metal dusting damage is protective coatings and surface treatments. Number A, ceramic coatings. Application of ceramic coatings is onto thermal spray coatings of alumina, zirconia, or other ceramics act as barriers. Advantages of ceramic coatings is high temperature stability, low permeability to hydrocarbons. Number B, contaminant removal. Aluminized or chromized coatings. These forms of surface alloying create protective oxide layers in situ. Number C, surface finishing. Smooth, clean surfaces. Reducing surface imperfections minimizes initiation sites for pitting and corrosion. Number 5 of the prevention and mitigation strategies of metal dusting damage is operational and maintenance strategies. Number A, regular inspection and monitoring, using the following methods. The first method is visual inspection, detect early signs of surface degradation or spallation. The second method is non-destructive testing such as ultrasonic testing, eddy-current, or thermography to identify thinning or cracks. The third is sampling and microstructural analysis, detect carbide depletion zones or internal voids. Number B, cleaning and surface treatments. Cleaning, remove carbonaceous deposits that promote carburization. Passivation, applying passivation treatments to enhance oxide stability. Number C, replacement and repair. Component replacement, timely replacement of heavily damaged parts. Coating repair, recoating or reapplication of protective layers. Number 6 of the prevention and mitigation strategies of metal dusting damage is design modifications. Number A, geometrical design such as the following. Minimize sharp bends and joints, reducing crevices where hydrocarbons can accumulate. Ease of inspection and maintenance, design for accessibility to facilitate early detection. Number B, use of barriers, insulation and shields, physical barriers to prevent direct contact with hydrocarbons. Summary of metal dusting damage prevention and mitigation strategies. If the strategy is material selection, described as use resistant alloys, coatings, it is purposed to reduce susceptibility. If the strategy is temperature control, described as keep below critical temperatures, it is purposed to minimize carburization risk. If the strategy is process optimization, described as adjust flow, composition, it is purposed to reduce hydrocarbon exposure. If the strategy is environmental control, described as inert or oxidizing atmospheres, it is purposed to protect surface integrity. If the strategy is surface treatments, described as ceramic or metal coatings, it is purposed to create physical barriers. If the strategy is monitoring and maintenance, described as regular inspection cleaning, it is purposed to detect early, prevent failure. If the strategy is design optimization, described as geometrical improvements, it is purposed to minimize areas prone to damage. Preventing metal dusting requires an integrated approach combining material science, process engineering, and maintenance practices. Tailoring these strategies to specific operational conditions greatly enhances equipment longevity and safety. Metal dusting damage inspection and monitoring based on API 571. Number 8. For heater tubes with suspected damage, compression wave ultrasonic testing is probably the most efficient method of inspection since large areas can be inspected relatively quickly. Number B. RT techniques can be employed to look for pitting and wall thinning. Number C. If internal surfaces are accessible, visual inspection is effective. Number D. Filtering the cooled furnace or reactor effluent may yield metal particles that are a telltale indication of a metal dusting problem upstream. Certainly. Here's a detailed overview of inspection and monitoring methods used to detect metal dusting damage. Overview. Early detection of metal dusting damage is critical to prevent catastrophic failure of components operating in high-temperature, hydrocarbon-rich environments. Multiple inspection techniques, both destructive and non-destructive, are employed to identify damage at various stages. Inspection and monitoring methods for detecting metal dusting damage. Number 1 is visual inspection, includes the following. Number A, surface examination, purpose to detect visible signs such as surface roughness, pitting, spallation, deposits, or discoloration. Procedure of surface examination are use magnifying lenses or borescopes for detailed surface views. And note areas with surface irregularities, cracks, or deposits. Limitations of surface examination is cannot detect subsurface damage or early-stage carbide depletion. Number B of visual inspection is surface cleaning. Method of surface cleaning is remove deposits and oxide layers via abrasive blasting or chemical cleaning to reveal underlying damage. Usefulness of surface cleaning method is improves visibility of surface features, pits, or cracks. Number 2 of the inspection and monitoring methods for detecting metal dusting damage is microscopic and microstructural analysis. Number A, optical microscopy. Application is to examine polished cross-sections to identify pits, cracks, voids, and carbide precipitates. The details is observe grain boundary degradation, carbide depletion zones, or internal cracks. And the limitations is limited to small areas and requires sample preparation. Number B, scanning electron microscopy or SEM. Application are onto high-resolution imaging of surface and microstructure, detect microcracks, carbide distribution, and oxide scales. Energy dispersive X-ray spectroscopy or EDS, elemental analysis to detect carbon-rich zones or depletion of alloying elements like chromium. Advantages of scanning electron microscopy or SEM, provides detailed morphological and compositional data. Number 3 of the inspection and monitoring methods for detecting metal dusting damage is non-destructive testing or NDT techniques. Number 8, ultrasonic testing or UT. Principle of UT is to detect internal discontinuities such as cracks or voids by sending high-frequency sound waves. Application of UT is to measure wall thinning and internal cracks. Limitations of UT is less sensitive to small surface features, requires access to component surfaces. Number B of NDT techniques is eddy current testing or ECT. Principle of ECT is uses electromagnetic induction to detect surface and near-surface flaws. Application of ECT is detects surface cracks, pits, or deposits. Advantages of ECT is fast, portable, suitable for routine inspections. Number C of NDT techniques is infrared thermography. Principle of infrared thermography is to detect temperature anomalies caused by internal cracks or voids. Application of infrared thermography is rapid screening for damage, especially in large components. Number D of NDT techniques is radiography, X-ray or gamma ray. Application of radiography techniques is to visualize internal features, voids, or cracks. Limitations of radiography techniques is less effective for surface features, requires safety precautions. Number 4 of the inspection and monitoring methods for detecting metal dusting damage is advanced and specialized techniques. Number A, microhardness testing. The purpose of the microhardness testing is to detect changes in hardness due to carbide depletion or carburization. Application of the microhardness testing is to sample microsections or indented to measure local hardness variations. Number B, auger electron spectroscopy or AES and X-ray photoelectron spectroscopy or XPS. It is applied as surface analysis to quantify chemical changes, carbon buildup, and oxide composition. Number C, thermal conductivity and resistance measurements. Its method is to measure changes in thermal properties that may indicate internal damage. Number 5 of the inspection and monitoring methods for detecting metal dusting damage is monitoring techniques. Number A, corrosion coupons and test pieces. It uses to expose test samples in operating environments and periodically retrieve for microscopic and chemical analysis, and the advantages provides real-time data on environmental aggressiveness and damage progression. Number B, sensors and embedded monitoring. Embedded strain gauges or crack sensors detect stress changes or crack initiation. Real-time gas sensors Monitor for increased levels of hydrocarbons or carbon monoxide indicative of damage. Number B. Periodic inspection schedules, routine visual and NDT checks based on operational history and risk assessment, data logging for trend analysis. Summary inspection and monitoring methods for detecting metal dusting damage. If method uses is visual inspection, it used to detect surface damage, deposits. The advantage is simple and quick, and the limitations is cannot detect subsurface damage early. If method uses is optical microscopy, it used to detect microstructural features. The advantage is detailed analysis, and the limitations is small area, sample prep needed. If method uses is scanning electron microscopy or SEM and energy dispersive X-ray spectroscopy or EDS, it used to detect microstructure, composition. The advantage is high resolution, and the limitations is costly, limited field of view. If method uses is ultrasonic testing, it used to detect internal cracks, wall thinning. The advantage is non-contact, deep, and the limitations is less sensitive to small surface cracks. If method uses is eddy current testing, it used to detect surface cracks, pits. The advantage is portable, fast, and the limitations is surface limitations. If method uses is radiography, it used to detect internal voids or cracks. The advantage is deep internal view, and the limitations is expensive, safety concerns. If method uses is microhardness testing, it used to detect carbide depletion. The advantage is quantitative, and the limitations is destructive, localized. If method uses is gas sensors and embedded devices, it used to detect environmental and structural health. The advantage is real-time data, and the limitations is complex setup. Conclusion: early detection relies on combining multiple inspection techniques. Routine monitoring helps track damage progression over time. Data analysis from inspections guides maintenance decisions and process adjustments.
Thank you.